afternoon, everyone, and welcome to today's webinar, a technical showcase of Netacea's development of cutting-edge bot detection technology. Leading today's webinar, we have Andy Still, Netacea's co-founder and CTO, and Matt Jackson, Netacea's head of data science. Andy is a pioneer of digital performance for online systems. As Chief Technology Officer, he leads the technical direction for Netacea's products, as well as providing consultancy and thought leadership to our clients. Andy has also authored several books on computing and web performance, application development, and non-human web traffic. So Matt achieved a PhD in particle physics on the Large Hadron Collider before working at several tech startups, where Matt applied his skills to solving commercial challenges. Matt now leads Netacea's data science team in their pioneering work in developing industry-leading bot detection technology. Okay, so over to you, Andy.
Thank you, Danny. So before we go into more details about how Netacea actually detects bot activity, I thought I would just do a quick introduction into what we actually mean when we talk about bot challenges and bot attacks on websites. So what's a bot? Bot is basically any traffic that is not triggered directly by human interactions by an automated process. There's obviously a wide range of bots that we see, and there's a lot of very good bots. So the internet as we know it today would not function without certain bots, so search engines being the most obvious examples of those. But there's also a very large amount of bad bots out there undertaking quite a lot of different threat activity against almost every website. So from the very obvious, things that are scraping content from websites using it elsewhere, to much more nefarious ones like people who are credential stuffing to try and actually take over account details, and kind of scalper bots and sneaker bots, which are borderline illegal, but certainly create a lot of brand damage and a lot of customer dissatisfaction. I think just before we go much further, I just wanted to highlight why bot activity is a different challenge to stopping general hacking activity. And the difference is it's a fairly fundamental one, though the actual people who undertake it may be a lot of the same people. Well, actually, what you're trying to do when you hack websites is you're trying to look for technology weaknesses, and you will send illegitimate interactions and activity to try and exploit those weaknesses. What bots are doing, as we will talk about them today, is actually sending fully legitimate requests into websites, but just looking to make those requests in an order or a combination that will exploit some of the business weaknesses within those websites. I'll just try and illustrate that with just an example of some of the complexity that bots are coming to these days. And we are seeing bots getting increasingly sophisticated, particularly around the way that they can hide themselves and the level of technology that they can actually use to exploit these weaknesses, and also the complexity in the ecosystem that's out there for people who are wanting to launch bot attacks. There's a whole range of available pieces of software, hardware, and even commercial services available to actually make the undertaking of these attacks much easier. So I'll just talk you through one example attack, and it's a relatively complex attack, which we'll go through the underlying complexity in a little more detail. But first, let's explain what the impact was, or the impact on the end user. So what these bots were doing was they were essentially targeting a particular website. They were managing to log in to that website as legitimate users who have an account with that website. They were then triggering a request for a refund on the grounds that the order had not arrived. That refund was being processed and being delivered as credit to that account. And what the last stage of that was, they were then placing a new order using that credit. So for the users who log in, they would see that one of their past orders has been refunded and an order had been placed on that account. That obviously led to quite a lot of loss of trust in the service that being provided. It was definitely an invasion of privacy, and there was a lot of worry about data. So there's a lot of brand damage going on. Obviously, from the website's point of view, they were losing the money, and they were having to supply that credit and fulfill that second order. So that's obviously a lot of damage to customers, customer trust, brand damage, and also financial damage. But what I think was interesting about this attack was when you look behind it, it's actually quite a complex attack that's been undertaken by probably a range of different people and a lot of different operators. And the way that attack will have worked is that it will have started with a data breach somewhere. It won't have been on the website that was being attacked. It will be on another website. That data will be breached and then shared through communities. So could be on the dark web. It could even be on the clear web. These data sets will be resold. Someone will get hold of that data and then will run a credential stuffing attack against the particular website they're targeting. And that credential stuffing attack will be fairly basic. It will just be running through a full set of probably thousands, if not millions of sets of credentials to determine where the user may have reused the credentials on the particular website that they want to target. At the end of that, they will end up with a much smaller set of credentials that are valid for a particular website. At that point, those credentials are probably then sold on again. So first actor gets some profit for targeting a particular website and sells on a set of valid credentials. The next actor will buy those credentials and actually look to target that a particular attack against a particular website. So they'll have identified that actually there's a weakness in the business logic here, that if I log on and I identify a particular type of order and I request a refund for that order, that refund will be processed automatically, and I will have then an account with an amount of credit that I can use to place future orders. And what you've then got is that you've got some credentials, and you will build a process to actually automate the refund of the order, so that you can then sell an account with known credit on it. And at that point, you sell those accounts, and the last step is quite likely undertaken by a human actor who actually manually goes in. He's bought an account with a certain amount of credit that they can use. He will then go on and place that order and actually undertake the final part of the fraud. So that last actor obviously takes the most risk to this, but it's been set up because there's this whole ecosystem of tooling and people and markets where you can share this kind of information. And I think what I wanted to get across with this is that actually what to the end user may look like quite a simple transaction, someone's got into an account and placed an order, is actually driven by this whole complex ecosystem of bot activity. And the reason why this is becoming ever more complicated, complex, is down to the fact that there's a lot of money to be made in this area. So the ecosystem bots is getting much more sophisticated, and it can just bypass most of the traditional bot defenses that were out there. The way that bots traditionally were detected was very much a client-side focused, worked on the assumption that bots were not executing requests in the same ways as humans were. So, for example, they would run some proof of work on JavaScript, just validated that it was an actual JavaScript-based real browser that was executing the request in the same way that a user would. They would build some kind of device fingerprinting, again, just looking to see that on the assumption that bots will be executed from servers, probably cloud-based servers. Humans will be using laptops or mobile devices. We can determine, the difference between those two. And then lastly, they'd start looking at things like, well, bots won't be moving a mouse in the same way as a human would. These kind of detections worked for a while, but as bots basically become much more powerful, they can mainly just bypass all those. There's all sorts of browser, you can execute from real browsers. There's techniques where you can fake the device that you're looking at, and you can even fake the interaction so that it appears much more human. Because they were obviously bypassed fairly easily, here at Netacea, we decided to take a completely different approach. Rather than looking at what was going on in the client, we looked at monitoring visitor activity on the server, where this obviously can't be faked, and it's where the interaction and the business logic is actually being executed. So if we can get to the core of that, we can determine whether or not it's actually malicious activity. What does that mean? Essentially, we'll build in a picture of what every visitor is doing. So looking at, does this visitor match some known attack patterns? Can we then categorize them as a bot? But what we need to do is look much more beyond the individual visitor. We'll actually look at what all the visitors are doing at the moment. Bots don't act alone. They would generally distribute an attack and come in as thousands or millions of different requests. So we look at grouping these visitor activity together into visitors doing similar activity, and then looking at unusual activity as well, because that's likely a new attack vector. Doing this does mean that we can detect bots a lot more accurately, but it has its own set of challenges. The main one of which is it's very, very large amounts of data. It's very complex to detect from that amount of data, particularly to do it in as timely a manner as you need to actually be able to react and stop bot attacks. So here at Netacea, this has been a journey that we've been going on to look at how we can effectively break down that large set of data into detection techniques that target specific types of bots, and we've developed quite a few of those in-house. And what we wanted to do today is just, I'll hand over to Matt in a minute to just talk you through the process that we go through to develop one of these new detection techniques, and the kind of way of thinking and the way that we develop those to make sure that we are actually targeting a new effective type of detection. So I'll just hand over to Matt now to take up this story.
Thanks, Andy. So as Andy just said, the bot landscape is rapidly developing, and here at Netacea, we try and detect these things server-side by looking at behaviors. So that is a challenge for the data science team from a technical point of view, because it's huge amounts of data that we want to kind of process in real time, but also from a development point of view, how do we quickly innovate and meet new challenges whilst providing a stable service to our customers. So today I'm going to talk through one such use case where we've developed a new technology alongside our existing technologies and solved a new problem for a customer. So the problem in question, a gaming site was wanting to stop odds scraping and R betting on their site. So this is when some actors try and gather odds across different websites, different platforms, and apply a win, lose, draw bet, for example, where they're always going to win because they've worked out the odds, and they can spread them across different parts of the site. So this is quite costly to the customer in terms of resources, because they're being scraped, but also in terms of their profits, because people are kind of gaming the system. So the problem for the data science team, we want to monitor the weblog data from this website, use analytics and machine learning to identify activity that's associated with this problem, and provide suggested mitigations to the customer to alleviate this. So in order to be successful as a data science team, like I mentioned before, we want to balance that kind of stable value and the kind of expectation of a customer that, we're experts at this, we stop bots, but also pushing the boundaries and constantly innovating to solve new problems and to develop our technology alongside the developing bot landscape. So as a data science team, to achieve this, we try and follow something called 3X methodology. So this is something that was pioneered by a guy called Kent Beck, who was heavily involved in Agile. He worked at Facebook, and essentially the idea is to, as quickly as possible, test new ideas, validate them with customers, and do all that before necessarily extracting a finished module or product, and validate it along the way, kind of like a fail-fast methodology. So throughout all this, collaboration with a customer is key, and that could be internal customers, so like our customer support or our development team, or it could be external. In this case, it's actually the customer. And throughout the process, we work with that customer to drive and validate the results. Today I'm going to be talking a little bit about something called footprinting, which is the solution to the aforementioned problem. So yeah, so a traditional approach to stopping something will be a classification model. So this is essentially taking a data set, labeling it. So it could be cat pictures and dog pictures, or in this case, it could be good traffic and bad traffic. Those labels would then get fed into a model alongside some engineered features. So a data science team would try and engineer features of that data that help discriminate between good traffic and bad traffic, whilst ensuring that the model is as general as possible, so it will catch lots of different cases. Throughout that journey, we'd kind of add some domain knowledge to provide the best possible recommendations for a particular customer. And then these models could get applied, and this is a pretty standard thing across most data science teams, to provide recommendations. So the plot here shows a really simple approach taken on this customer, and the purple line on the time series chart just shows all the mitigations that have been made using this approach throughout time. I think it's a couple of week period. And you can see there's kind of big spikes and there's kind of low level bot activity going on. On the right hand side, this particular part of development, we were just serving capture to the bots. There's a series of mitigations that could be served, but this is one way to get some idea how the model's performing. And you can see that the pie chart shows a big pink section of incomplete capture, which means the bot gave up, and a small amount of cookie fail. So this is when a bot has failed to pass capture. So the fact that these recommendations aren't leading to lots of capture pass gives some validation. So this is great, and clearly it's very useful as we're kind of providing that stable baseline, bot mitigation. But it's not always perfect, and we kind of think about it for this use case, but more generally as well. So the kind of questions that we'd ask as a data science team is, will this model always generalize for new data? So if the website changes, or we get a new customer, or there's a new attack type, does the model still work? We also worry around the labeled data set. So all the data that we receive is unlabeled. So to label a data set is actually quite a challenging problem in itself. And we want to make sure that those labels give a fair representation of actually what's happening. In this case as well, we can only label so much data. So we're not leveraging a huge amount of unlabeled data. And when I say huge, like the data sets we have are massive. So it's also a challenge to leverage information stored in broad categorical features. So you imagine the request path, the user journey and how someone interacts with them paths is really interesting. That's the behavior. But to turn that into a numerical feature to use in these models can be really, really challenging. And then finally, and I think in this case, this is a particularly important point, that the most powerful features to distinguish the scraping behavior seen on the previous side are often based on aggregations over time. So, these are longer term behaviors, which are easier to spot the longer window you look at. But that adds latency to the recommendations, and isn't always the desired outcome for the customer. And in this case, we wanted to stop things as quickly as possible. So this set us up with a new challenge for this customer, and we entered the first X of the 3X methodology, explore. So at this point, we have a problem statement. We've not built anything beyond our standard offering. So there's really kind of no risk, and we can, as a data science team, just go wild and try a load of different experiments. So I always think of it as throwing spaghetti at the wall and seeing if anything sticks. We couldn't do this if it was a fully developed feature, because there'd be too much tech debt and all that kind of stuff. So it's getting in there really early and figuring out what we're trying to solve. So the kind of challenges we were exploring here is, can we identify this scraping in our betting behavior in real time? That was really important. Are we able to utilize all that unlabeled data and get some benefit from it? Can we leverage the categorical features beyond how we already do? And how could we ensure that the results will be consistent? So although this is a specific use case, kind of in the back of our heads, we're always trying to think, how can we make this general? How will this apply in the future to other customers? And that's a kind of constant to and fro. So the idea that actually stuck to the wall, I guess, is this one. So I've already mentioned that when we're talking through behaviors, actually as a human, sometimes just looking at the web logs and looking at the order and the paths hit is where the rich information is gained. And even as a human, that can be quite tricky. So we were thinking, how can we represent this numerically, and how could we use it as a feature in this model? And the idea was that this problem is potentially analogous to something in natural language processing. So NLP is machine learning for language, essentially. And we can see this better on the next slide. So in NLP, we would have an entity called a token, and this will be a word. So for example, orangutan. The sequence of these words, or a sentence, could be something like the orangutan ate orangutan. And that kind of translates into a vocabulary. So the English language has 170,000 words thereabouts. And the problem in NLP is representing that numerically to do something, for example, like suggest a sentiment of a tweet. So if we compare this to web traffic, a request or a path is kind of like a word or a token. The sequence of those requests is somewhat like a sentence. There's context there, there's syntactically similar paths. So you could be traversing an e-commerce website, you might log in, you'd go to a product page, maybe you go to TV, and a TV page might be syntactically similar to a radio page, and kind of all these things that add up into this sentence of the user journey. Coincidentally, a typical website is probably in line with a vocabulary of a language. So a typical e-commerce website, we might see around to the order of 100,000 paths. And we have exactly the same problem. So we want to represent this session numerically and classify an outcome based on that. So we ran with it. Thankfully for us, this is kind of like a pretty well solved problem in NLP. So we took that idea and tried to apply it to our use case. The next 3 slides, I'm going to try and explain how that is done in NLP fairly briefly. So the first stage is, how can words be represented numerically? So our tokens. And the kind of entry point here, and the most simple way to do this, is through one-hot encoding. So if we take a really, really, really simple vocabulary of 3 words, so we have orangutan, ate, and rambutan, they can be translated into these one-hot vectors, where each word has an index on that vector. So orangutan has the first index here, and it is assigned a 1 there and zeros elsewhere. Ate, the second index, and the others are zeros, and rambutan, the third index, and all the others are zeros. So this is really great if you've got 3 words. If you've got 100,000 words, you can imagine all of the zeros in that, and you stack that up to your vocabulary, and you've got a huge sparse matrix, which is not technically very fun or useful to work with. I think that's only the start of the issues. So if we move on to sentences, we might take the one hot encoded vectors, and we might use something like the bag of words method. So here, you just maybe count the word frequencies within a sentence. And this leads to problems such as words having no context. So we're representing them as a number, but the number doesn't really give any context to the sentence. And this is probably most easily demonstrated by just comparing the two sentences. So we could take our vocab and write a sentence. The orangutan ate orambutan, which is probably okay. I don't know if they eat that fruit, but you could see an orangutan eating a piece of fruit. We add up the frequencies from our vectors, and the sentence is represented by a vector of 1, 1, 1. The sentence, the orangutan ate an orangutan, which is slightly more ridiculous, is actually represented in exactly the same way. So in our use case, when we're thinking about user behavior, this kind of leads to some issues and doesn't really capture what we want to know. But thankfully, we can use a technique called word embeddings. So I'm not going to go into a lot of details about this whole network, but the idea is that a neural network is trained with a toy problem. And that toy problem says, given a load of training data, which is sentences, if we pick a starting token, so any word in our vocabulary, can we predict the next word in the sentence or a word within a window of that word in our training data? This network is trained, and eventually, if it's trained well, we'll have a machine learning model that, given an input word, can predict what the next word in a sentence is, which is kind of fun, but not that useful. The really cool bit is that the hidden layers in the neural network, as it learned, developed some vectors which have numbers assigned to them. We'd refer to them as the weights of the network. And it's actually these learned weights which then represent our vocabulary. So the result of training this model is a numerical vector for each word in your vocabulary. And you hope that the information about the words and their context within language is embedded. We can see that this works in natural language processing, and it's very heavily used, a very heavily used technique, and they're extremely powerful. So I would recommend this to everyone. Just go and Google word2vec or word embeddings and look at some of this, because it's unbelievable how powerful it is. But there's just some examples here. So on the bottom of here, there's kind of a representation of those numerical vectors in a 3D space. But the thing that is really cool is how those vectors encapsulate the context and the differences between the words. So if we just look at the male-female bit, you can see like the distance and direction from king to queen is the same from man to woman. And you can even do arithmetic on these vectors and kind of calculate what's king minus man add woman, for example, and you'd end up with the vector for queen. So they're really powerful, and they solve some of the problems in the one hot encoding and bag of words, because we're actually learning about the words and how they interact with each other. So the question is for the data science team in this exploration is, did it hold for paths? And the answer, at least anecdotally at first, was yes, they do. So this nice GIF on the right-hand side shows all of our paths embedded using the word embedding techniques, and how they're represented in that 3-dimensional space. So the really cool thing is that we can see these kind of clusters forming, and the clusters of paths, at least at first, again, subjectively, we're kind of of similar context, and they were closely related. So that gave us a lot of evidence that this was a good technique to use. So we just kind of reverse a little bit and think about what our problems were, and if this technique might solve them. So can we identify the behavior in real time? So we think we can extend the path embeddings technique to user sessions. And we know that these user sessions are ingested in our pipeline in real time, and we can update the embeddings too. So, that is one problem solved. How can we utilize this huge amounts of unlabeled data? So all of the data is used to train session embeddings. It is unlabeled data, and that goes into the model as I described before, like the training data from the word embeddings would just be our weblog data. So we actually leverage all of that data and pull out those similarities between the paths. Can we leverage the categorical features locked into the requests? Well, yes, I've just shown that the path, its relationship to other paths, all that is captured within the embedding. And how can we ensure results are consistent across domains? I think each domain or each problem will have its own vocabulary, and specific models can be trained for that. So I think it solves all of the problems that we set out, which brings us to the next X. So the second X in 3X is expand. So we've got some spaghetti stuck to the wall. We're really excited about it, and we want to get some buy-in from a customer, again, internally or externally, and think, how can we provide value using this and expand the kind of proof of concept of the idea into a usable product feature, whilst providing that kind of baseline service to the customer. So what we decided to do in this case is we knew we were getting value from the classifiers. So keep providing that value to the customer, and then work with the customer to target behavior, which is repeated and syntactically similar behavior. For example, odd scraping, that we could try and stop in real time using this new footprinting method. So now we can see some results of this. So this first use case was the one described before with the gaming site. And we think that the footprinting will work well because it's not necessarily high volumes that we're trying to stop now. We've stopped a lot of that, but they are using kind of a varied yet syntactically similar approach. So we work with the customer to identify the candidate footprint, so these sessions and types of behavior we want to block. And we tested this basic approach and built a solution using the customer to feedback. And this slide shows the initial results. So the plot in the bottom left, the blue line shows the requests which weren't blocked. So this is all of the requests on the website over a couple of weeks. The orange line shows the things that were blocked, and then the green line just shows a percentage of that. You can see the percentage on the right-hand side y-axis. So the first thing to call out is there's quite a lot of malicious behavior on the site that we're able to block. But for the data science team, what was really exciting was this pie chart on the right. So if you think back to before, we demonstrated that the initial approaches were blocking quite a lot of traffic. But then when we apply footprinting, we can see that the footprinting technique actually picks up a whole lot more. So here the footprinting is in the dark blue, and the kind of existing methods demonstrated before are in the orange or light blue. So this was a really great validation that this solution was built for a customer, was solving their problem. And the feedback from the customer has been great, and it really has solved their problem. So yeah, so this is kind of the results for the business use. So the reduction in total website requests was 40%, which translates to an overall saving of around 3 million. And that is, as we said before, across the infrastructure of the website, the fraud losses and the staff that have to deal with that off the back of it. And it also provided an 85% reduction in unwanted bets placed by bots. So real success story with that one. But this talks about data science and how we develop these things. So great, we've solved a problem for our customer. But really our motivation is to solve general problems and build a product that can solve these things on day one. So we continued our expansion of this idea and applied it to a different use case. So this second use case, we have a content provider, and they're being targeted by bots that are trying to skew the ad spend by clicking on certain links throughout the site and all that kind of stuff. So again, it's highly targeted behavior. It's not traditional scraping behavior like maybe some of the odd scraping was, but it has this very syntactically similar approach. And we thought, you know what, this is the perfect use case for this technology we've developed. So during onboarding, we worked with the customer to identify some suitable behaviors that this could be used for. And we used the existing service that would built for the first use case to provide the recommendations. And here we can see the results for this second use case. So the plot on the left, the shaded green area is the total traffic seen on the site. And what you'll notice from that is there's these huge spikes of what actually was some of this targeted behavior. The solid red line shows the resulting traffic after the real-time models were applied. So this is really cool that, this is not just reducing those spikes and kind of flattening the general traffic patterns, but this is actually in real time as well. And further to that, one way that we can try and validate internally how this is acting, we can look at what is the traffic that we're blocking. And I think although this is just a high level method, I think it's quite nice to demonstrate the success of this. So bearing in mind that this technique has no context around who is doing the attack, it is purely based on the behaviors of the attack. We can see in this pie chart on the right, we have the outer ring, which shows the percentage of traffic blocked by the 4 candidate footprints we've identified. And then internal to that, it shows how much of that traffic was coming from data centers that we suspect would traditionally be okay. So like home broadband providers. And the caveat here is, of course, an attack could be launched through a botnet or just from someone's laptop. So it's not always true. But the really nice thing is that the majority of this is light orange, which is from kind of data centers which we treat with more suspicion. So even without the context, we've reduced the behavior happening, and we're seeing it's coming from potentially bad sources. Add the feedback from the customer into that, and it really validates this approach as a really exciting result for the data science team. So finally, we'll move on to the third X, which is extract. So throughout the process, we've kind of worked with customers to rapidly develop this prototype and expand it into something that is usable and useful. And that, that process can be quite scary as a data scientist, because the longer it goes on and the longer it's successful for, the more risk is building, because people are bought in and you're providing a service. Eventually you'll get to a point where there's a known set of requirements. So working with the customer and from a technical point of view, we understand what are the limitations of the system, how does it work, how does it fit in, and we'll move to extract a useful product feature that can then be applied to additional customers without going through that whole 3x innovation cycle. And it might be that we need to expand that into something else in the future, and we can kick off that innovation all over again. So just to conclude, I think we can say that this 3x approach, we're able to explore challenging problems. We can develop unique patented solutions. So footprinting is completely our own technology. We've provided value throughout that journey to customers. And I think building trust and relationships as well is really important. And then off the back of that, we've extracted a useful system that future customers can use to solve similar problems. So, you know, for a data science team and hopefully for the customers, it's a win-win, really.
So you explained there 2 use cases of the application of footprinting technology. Has the technology been applied to any other use cases so far? And I suppose if not, how can you foresee it being applied in the future?
Yeah, so I think kind of hopefully it was evident throughout that talk maybe what this was useful at spotting, and that's like kind of like more targeted, repeatable kind of behaviors. So that kind of matches a lot of customers. So you can think things like product scraping, stuff like that. This fits really nicely into. And then when we onboard new customers, there may be other use cases like the ad SKU that we talked about previously was an example of this, where we identified this is a really good solution to use for this customer. So we'll turn that service on for them.
Great. That's, yeah. The articulation of the 3X methodology was really interesting, especially going through the was it explore that's first, and then finding out what sticks. It makes a lot of sense. Thank you both for taking us through, for Andy for taking us through the current bot landscape today, and Matt for the technical showcase of our latest bot detection technology. So if you've enjoyed today's webinar, please do, and it's got the cogs whirring with any questions you might have about our bot detection technology, or even if it's made you more intrigued about your own bot management strategy, please do get in touch with us at hello@netacea.com, or visit our website and have a little look at what it is that we are, how our product is developing, and any other resources that might be useful to your own research. Thank you for joining us, and we hope to see everybody again soon.